Welcome back to the video series here in Algebra 2 Trig. This is section 8.5, the remainder and factor theorems. We're going to build upon what you did with synthetic division and expand it to using it towards general polynomials. We're going to use the remainder theorem to find factors and remainders of polynomial functions, and we're going to learn and use the factor theorem and use synthetic substitution to find factors of polynomial equations. How do we do that? Well, stay tuned and we'll see. So let's take a look at example 1. Find p of x equals x cubed plus 2x squared minus x plus 4 when x equals negative 5. Now if I wanted to know what p of negative 5 was, all you would have to do is take this negative 5 value and plug it into x and solve for p of negative 5. So you plug in negative 5 for x, and if you simplify it, you end up with negative 66. Now, there are other ways to do this, and we're going to be using synthetic substitution to do that, and we'll show you how to do that. If you were dividing a polynomial p of x by x minus c, you would get this. So when we divided the polynomial p of x by x minus c, we got this q of x. That's the quotient. That's what we got either on top of the long division or using the coefficients after we did synthetic division, plus the remainder divided by x minus c, where q of x is some polynomial with a degree n minus 1. So if p of x was x to the fourth has its highest term or its degree, q of x's highest term would be x cubed. P of x was x to the sixth, q of x would have an x to the fifth, and so on. Now, if we multiply both sides by x minus c, you get what is called the remainder theorem. So, let p of x be a polynomial a positive degree n. Then for any number c, p of x is equal to q of x times q minus c plus r, where q of x is a polynomial degree n minus 1. So all we did from the previous slide is multiply every term by x minus c. This left us a p of x over here. Q of x is now multiplied by x minus c, and we have a plus r. So this r ends up being the remainder theorem. And when you plug in any value of x, r is going to be that value of the function at whatever value of x you put in. So here is our remainder theorem. P of x equals q of x times x minus c plus r. And if c equals x, then the q of x term is 0, and the only thing you're left with is r. So if you plug in c for x, this is 0, so q of x times 0 is 0, and the only thing you're left with is r. And that's the idea behind the remainder theorem. C is what you're putting into the equation. And let's take a look at how this works in example 1 using synthetic substitution. P of x is equal to the remainder r when p of x is divided by x minus c. So, if you wanted to find the remainder of p of x equals x cubed plus 2x squared minus x plus 4 when divided by x plus 5, we could use synthetic division using c equals negative 5 to find the remainder. And by doing so, we actually find out the value of p of x for x equaling negative 5. So again, what synthetic substitution does is you can use synthetic division, plug in the c value here, in this case it's negative 5, and when you run it through, the remainder is the value of the function at the value of c you put in. So here's example 1. Here our c is negative 5, so we stick that in the left corner. We bring our coefficients down, so we have 1 for x cubed, 2 for 2x squared, negative 1 for negative x, and 4. And now all we do is do synthetic division. So you bring down the 1, multiply 1 times negative 5, which gives us a negative 5 there. 2 plus negative 5 is negative 3. Negative 3 times negative 5 is 15. Negative 1 plus 15 is is positive 14. 14 times negative 5 is negative 70. So our remainder is negative 66, which matches what we got in the function when we actually plugged in negative 5 for x and the x cubed and the x squared and the x expression. So notice that when the remainder is the same, when we plugged in negative 5. So the point of synthetic substitution and the remainder theorem is that you can figure out the value of a function for any value of x by changing that value to a c and running the synthetic substitution. The remainder will provide you the value of the function when you plug in that value for x. So it's pretty handy, and that way you can save yourself the work of figuring out the third power of -5 or whatever. This leads us to the factor theorem. The polynomial p of x has x minus r as a factor if and only if r is a root of the equation p of x equals 0. Now this isn't anything different that we've already done. If x is a root, it's going to make the function 0. So if it's k plus radical 3 a factor of p of k equaling k cubed plus 2k squared minus 3k minus 6. So one way you can do it is to plug in radical 3 for k in every value. But what we can do now is use synthetic substitution. Figure out what the c value is and use synthetic substitution to see if it is a factor. If our remainder is 0, and this is the key thing, if the remainder is 0, then this is a factor. So we plug in k plus radical 3, and if we get a 0, then we know it's a factor. I just said that. So what is c in this case? Well, since it's k plus radical 3, c is actually negative radical 3. So we're going to plug this in into our synthetic substitution module. So here it is. And it's a little messy because you have a radical, and you might be thinking, gosh, it'd just be easier to plug in radical 3 over there. Yeah, you could do that, but what that doesn't give you is what's left, and we're going to be using that later on in this section. So bring down the coefficients, 1, 2, -3, -6, and run the synthetic division. So 1 times negative radical 3 is negative radical 3. 2 minus radical 3 is just that. Now multiply this quantity by negative radical 3. So this gets you 3, which is negative radical 3 times negative radical 3, minus 2 radical 3. Add those together, you get just a negative 2 root 3. Multiply those together, and you get 6. And lo and behold, the remainder is 0. Therefore, k plus radical 3 is a factor of k cubed plus 2k squared minus 3k minus 6. Now again, you're probably wondering, why don't I just plug in negative radical 3 into here and solve to see what the function is? That does work, but then you lose this information here, because this information would help you solve for other factors later on. Example 3. Find a polynomial whose roots are 0 and a double root of -1. So when we did the equation in chapter 7, we knew how to find the polynomial when we had 2 roots. But what if you had 3 in this case? So p of x, this function, must have x minus 0 as one of the factors because 0 is a root, and x plus 1 squared as 2 other factors because -1 is a double root. So x plus 1 must appear twice in the function. So now we put that all together. P of x equals x minus 0 or x times x plus 1 squared. And now all you do is multiply it out. So x plus 1 squared is x squared plus 2x plus 1. And we distribute the x. So the answer to example 3 is x cubed plus 2x squared plus x. So to find a polynomial who has different roots, you can just create the factors and work backwards. So the factors are x minus each root. And in this case, since there's a double root, there are going to be 2 of these factors. Now the concept of a depressed equation. It's sad. It's depressed. Suppose you are given one root r of the nth degree polynomial equation p of x equals 0. Thus, by the remainder and factor theorems, p of x equals q of x times x minus r. You can find the remaining roots by solving the depressed equation q of x equals 0. So let me explain what's happening here. Let's say you are told that one of the roots of your equation is r, which means x minus r is one of the factors. What you can do is then use synthetic division to figure out what q of x are. Q of x is. That's the remaining equation after you divide by x minus r. Then you could take q of x and solve for that equation. Solve the remaining roots. Q of x here is the depressed equation. It's the equation that you're left with after you divide the original polynomial by x minus r. And you can do that because you know r is one of the roots of the equation. So let's see how this works in example 4. Solve 3x cubed minus x squared minus 18x plus 6 equals 0, given that 1/3 is a root. So what you have to do is use synthetic substitution, plug in 1/3, churn it out. You should get a remainder of 0, and whatever's left, you're going to solve that equation and get the other roots. So first, Find the depressed equation by dividing p of x by x minus 1/3. Since 1/3 is a root, we know x minus 1/3 has to be a factor. And so we can divide this by this, but you might as well use synthetic division because it's a little cleaner. So if we set up our synthetic division, 1/3 is our value for c. Bring down the coefficients of the polynomial, 3, -1, -18, and 6, and just go through it. And I'm going to go through it very fast because you guys can do this, and if you need to stop and slow down, go right ahead. And as expected, you get 0. Now, in the previous example, if you just wanted to find out something was a root, you could just plug it in, but then you don't get the remaining equation after you divide. So the depressed equation in this case, the equation you get after dividing this polynomial 3x cubed minus x squared minus 18x plus 6 by x minus 1/3, which you know is a factor because we were told 1/3 is a root. The remaining equation, the depressed equation, is 3x squared minus 18 equals 0. Now, what you do with this one is you factor that one and you solve for x to get the other two roots. So you can divide both sides by 6 to get x squared minus 6 equals 0. So x is equal to plus or minus the square root of 6. So now the complete solution to the polynomial in example 4 is 1/3 radical 6 and negative radical 6. So what you can do with the remainder theorem and the factor theorem, if you are given one of the roots, divide the polynomial by that root and take whatever the remainder is, not the remainder, the quotient, and solve that equation to solve the remaining roots. And we'll be doing that in greater extent in 8.6 and 8.7 because the examples in this section are relatively easy. Alright, the last two examples I would like you to do on your own. Start with example 5. Example 5 asks to see if b minus 4 is a factor of b cubed minus 5b squared minus 2b minus 8. And I also want to know what the depressed equation is after you figure that out. If it is indeed a factor. If it's not a factor, you'll have a remainder. And then also do number 6. Use the factor theorem and depressed equation to solve the equation in number 6, given that 3 is one of the roots. So go ahead and do both of those, and you can check back here to check to see if you did them correctly. Alright, so to set up the synthetic substitution, we put in c equaling 4, and we set up our coefficients as such, 1, -5, -2, -8. And again, I'm going to go through this quickly so that you can get on with your life. And unfortunately, the remainder is -32. So b minus 4 is not a factor of b cubed minus 5b squared minus 2b minus 8. If it were a factor, the remainder would be 0. And again, by the remainder theorem, if you plugged in 4 to this equation, you would end up with -32. And that's what the remainder theorem says. So it's a multifaceted equation. Finally, number 6, use the factor theorem and depressed equation to solve 2y cubed minus 5y squared minus 4y plus 3, given that 3 is one of the roots of the equation. So, again, you're going to use synthetic substitution. You are going to use 3 as the value for c and divide. And whatever you get here will be the depressed equation. You will have to solve that equation for y and get the remaining two roots. So bring down the coefficients for the original polynomial and go ahead and do this synthetic division. And I will do them quickly here. And sure enough, we get a remainder of 0. If you do not get a remainder of 0, when they tell you that a certain number is one of the roots, either A, you did this part wrong, or B, I screwed up when I asked you the question. Alright, so the depressed equation in this case, what is it? It is whatever you get from these coefficients. 2y squared plus y minus 1 equals 0. So now you have to take this equation and solve for y. And those will provide you the other two roots aside from 3. So you can do this any way you want. You can complete the square, you can use the quadratic formula, or you can just simply factor 2y minus 1 times y plus 1 equals 0. So y equals 1/2 or y equals -1. So again, the complete solution using the factor theorem and then factoring 3, 1/2, and -1. You got 3 because it was given to you. You use synthetic substitution to figure out the depressed equation, and then you solve the depressed equation to find the remaining two roots. So going back to our goals, the remainder when a polynomial p of x is divided by x minus c is simply p of c. So if you divide p of x divided by p x minus c, the remainder is the same as had you plugged in c for x. This can be done using synthetic substitution. Solve equations with the root by using synthetic division to find the depressed equation. Again, the depressed equation is the equation you get, the quotient, after you divide a polynomial by a known root, and then solve for the remaining roots. That's it for section 8.5. You will be doing problems in class tomorrow while I'm gone.